I'm going to talk about embedded Linux and what it means to me, and how I dislike talking about embedded Linux and the mainline kernel and how to work with it. Oh, come on, talk to me. Please? I'm going to talk about OpenOffice and how I hate it. Hey! So, Linux is everywhere. You see it on all kinds of devices, control devices, phones, all the way up to supercomputers, mainframes. Everybody runs Linux. And we talk about embedded Linux, but what does it mean? You know, some people talk about embedded Linux and they include this kind of thing. It doesn't have a screen and a keyboard. It doesn't have a user with a graphical desktop. It must be embedded, right? So we use the term embedded Linux to cover all manner of evils. And a lot of the time when you hear sort of people in the Linux development community talking about embedded Linux, mostly it's a code word for stuff we don't want to have to care about. But it's increasingly important. I mean, there are millions of Android devices out there really, pushing the focus on embedded Linux so a lot more people admit that we have to care about it than used to admit this. And we can consider a lot of things to be embedded, even up to perhaps devices like netbooks, ultrabooks, tablets. They aren't necessarily the typical thing that you might have thought of when you think about embedded Linux, but they have a lot of the same requirements. So what makes an embedded device? Is it the fact that it's headless, that it doesn't have a screen and a keyboard? Is it the fact that it's handheld, battery-powered, cares about power management deeply? Is it the physical size? I mean, is it the constraints of the hardware, the RAM, the storage, the CPU? What else makes embedded? What do you think? Dedicated usage? Yes, that's common. That's a common criterion, isn't it? Yes. So my Mac G5 is embedded. Actually, it is. I moved a month ago. It's still packed in boxes. But, yeah, non-x86, that's common. Anything else?
No X11.
Sorry?
No X11.
No X11. Yes, that's true. So there are all kinds of things that people mean when they talk about embedded Linux. But there are a number of things that are quite common. Power management is a very common requirement. When people talk about embedded Linux, often they think of power management. We need to conserve battery at all costs. We need to shut down any circuitry which isn't in use right now. We need aggressive runtime power management. We also think about fast startup. You take your phone out of your pocket, you turn it on. There are legal requirements about how soon you must be able to make an emergency call. And even in consumer devices outside that, you have to be able to get a consumer experience quickly when they turn a device on. And that's one of the things that people care about a lot when they talk about embedded Linux. Again, headless operation, we covered this, didn't we? No X11. Sometimes, no user interface at all when it's just an embedded control device, a router, something like that. But we care about, where we do have a user interface, we care about having clean user interfaces. User interfaces that work on a small screen, that work with a touch screen. And that's a common theme as well. And we care about solid-state storage. I'm not going to go into any more detail about solid-state storage, don't worry. So these are our needs, but they're not specific to embedded Linux. None of them are specific to embedded Linux. Everybody else needs these. There is actually a huge crossover between what we need in the embedded space and what people doing big iron want as well. So let's take a look at power management. We care about it for embedded for battery life. We want to make our devices last as long as possible before they shut down. But in a data center with huge racks of machines running a server farm, what do you care about? You care about power management, because you don't want to be running at full cost, running everything at full tilt, paying for the electricity to waste heat, paying for the electricity to run your air conditioning at full blast to get the heat out of the building again, so you're paying for it twice. And so actually, the power management requirement, all the requirement for runtime power management on Linux systems, this isn't an embedded requirement at all. This is something that everybody cares about. And nowadays, they're starting to realize they do. So we're seeing a lot more acceptance of this kind of requirement, and we've seen some very good work going into the Linux kernel recently on power management, where maybe 10 years ago there was a lot more resistance from upstream with people saying, oh, we don't care about this kind of thing, why would we care? So tickless operation, we heard about tickless kernel earlier. And yes, this is really useful. It gives us big power savings when we're running on battery, when we don't have to wake up the CPU every thousandth of a second, hundredth of a second, and do stuff just to realize that we can go back to sleep again. So that's great. That's an embedded requirement. But it's not just an embedded requirement. If you think about big farms of virtual servers, the big hosting farms running lots of virtual machines, they absolutely do not want every virtual machine, every one of thousands of virtual machines waking up every millisecond and doing all this gratuitous stuff just to go back to sleep again, because that means the hypervisor has then got to run every single virtual machine, and the cost of that is insane. You can actually have a physical hardware with a hypervisor doing nothing but running the timer tick on thousands of virtual machines and having no time to do any real work. So again, we have tickless operation, which is not just an embedded requirement, it's something that we need everywhere. Fast boot. So I talked about this. We have requirements for mobile phones that you have to be able to make calls within a certain amount of time. And it's just a very important user experience requirement for many tablet devices, ultrabooks, etc. We care deeply about fast boot. There's been a lot of work going into Linux distributions to make sure that it boots fast, it gets you to the login screen or to the working environment as quickly as possible. But you might guess where I'm going with this. Big Iron needs it too. If you've got a server hosting some service and you've promised 99.999% availability, how many seconds a year are you allowed to be down? That's less than one reboot. You need to reboot. If you have to reboot, you're eating into your uptime guarantee very, very quickly. So you need your servers to come back quickly. And so fast boot, again, is not just embedded. It's for everybody. Everybody cares.
Even on a netbook, you say?
Yeah, everybody. Absolutely. Yeah, I care if I get up to the front here, boot up my laptop, and you're waiting for 5 minutes while it boots up and I can't do my presentation. Or if you're waiting for 5 minutes while we try and drive OpenOffice. Yeah, absolutely. Everybody cares. There's nothing that is solely an embedded concern. And user interfaces as well. There are some specific requirements for sort of handheld touchscreens, but really these also cross the board. And we've seen, I know GNOME 3 isn't very popular, but a lot of the concepts do actually make a lot of sense. And we've seen that user interface development driven to a certain extent by requirements elsewhere. So yeah, netbooks in particular need sort of the uncluttered user environment. And so there is so much that is just not a requirement for embedded. This is why I don't like talking about embedded Linux. I like to think there is no such thing as embedded Linux. There is just Linux. So flash storage, we have flash storage in embedded devices, but we are increasingly seeing SSDs in laptops, even in servers. So again, despite me saying earlier, I like to see proper flash access in embedded devices, we do seem to be moving towards more and more embedded devices, even new Android devices, having the fake disk, an SSD, an SD card. And so essentially that's the same kind of technology from the embedded device all the way up to the big iron. And so we care about the same things, that, getting trim working, getting the device sleep working, all the things that allow us to work around the problems of the pretend to be a disk approach. We care about that everywhere from...
Is the firmware inside such a device in Linux kernel? I believe not, but I don't know.
Sorry, what was the question?
Is the firmware inside such a device in Linux kernel?
Inside an SSD? No. It'll be a microkernel of some kind, a tiny RTOS of some kind. It's very... You could do, but it's very unlikely to be a Linux kernel. But there are as many answers to that question as there are different SSDs from different vendors, of course. But basically, I don't know of any of them that would be using Linux. Linux is a good fit for many things, but that isn't one of the things that Linux is great at. In fact, I spent a lot of time saying that in the early days of embedded Linux. Yes, we love Linux, but don't try to use it for this. And that is one of those, I think. Prod. So, execute in place. In the days of NOR flash, which could be mapped as ROM, and just you could access, the CPU could access the data directly and run code from it directly, it was very useful to have execute in place support, so that rather than copying your code, your kernel, whatever, from flash into RAM and running it from there, you could actually run it in place. This meant that on a tiny device, you could get away with a lot less RAM and a much faster startup time at a cost of the fact that running from flash will be slower, just because RAM goes faster. So execute in place was really useful for that. But in fact, it turns out that execute in place and all the horrible tricks we have to play in the VM to map this page here of this physical thing that isn't RAM, map it in as a page of page cache, a page of a file, etc. That's really useful for virtualization as well. So the support which actually eventually gave us execute in place support in the kernel did not come from embedded developers. It came from IBM working on S390, so that their virtual machines could share underlying disk devices and map, basically the host, the hypervisor, would load a page from the disk into RAM, and that physical page would then be shared into all the virtual machines using the same execute in place methodology throughout the Linux virtual memory system. So again, it's not just embedded.
So isn't it more a hardware issue than a software one?
It has to be supported by the hardware, yes, but there is a software issue in that the virtual memory management system in Linux has to be able to cope with the fact that we're not just managing standard pages of RAM that can be read and written to, made dirty, and then written back to disk, which is basically how all the memory management worked, with flags on pages to mark them as dirty and needing write back, etc. You had to cope with the fact that actually what I'm doing here is when user space memory maps a bit of a file, I am giving them physical access directly to the original copy, which I must not write to. I cannot write to. It's ROM, essentially. And so if they're going to try to write to it, we then have to flip it into copy it into a page on in RAM and do copy on write, etc. So the complicated part of that was software. The hardware part, while necessary, from our point of view, that was simple. Either it's possible or it's not. if it's possible, then we have to do the software to cope, right? So the complicated part was the software, yeah. From the hardware point of view, in the embedded case of, ROM, execute in place from flash, the flash was there. There was a physical address for the flash, which was not RAM, and all you have to do is map it. But that was the complicated part, yeah. And DMA APIs. So, when you're using a peripheral to DMA to or from memory, a lot of the smaller systems had cache coherency issues, so that you had to make sure you flush the caches at the right time. Basically, it was a big problem for a lot of drivers, a lot of network drivers in particular, wouldn't get it right. They'd just say, right, here's your address, go and do it, and would fail when you put that same device into an embedded system. And they wouldn't use the DMA API properly, but we need them to, because bigger systems have an IOMMU now, so if you just pick a physical address from the ether and give it to your device, it won't work. So now we are seeing all the drivers being fixed to use the DMA API properly, so that they can work with current Intel AMD systems with IOMMU, and this means that those same drivers are fixed for the embedded use case, where we need to use the same API for different reasons. So it's just another case. I can't think of many things which really are embedded specific. We are not that special. I don't like talking about embedded Linux. I am one of the embedded Linux maintainers for my sins, but only under protest, because Andrew Morton kind of insisted on there being somebody to do that. And most of what I do in that role, which is very, very little, is to say, this is not embedded, this is, this is generic. So, to a certain extent, as I said earlier, people think of embedded Linux, the embedded Linux community. The mainstream kernel development, Linux development, thinks of enterprise and embedded in much the same way. It's just that stuff we don't want to have to think about. They like to think of embedded developers as working with ancient code that nobody cares about anymore, not working with upstream, doing their own thing, going off into the weeds, not contributing their code back upstream, doing stuff as a one-off, making some hack, not attempting to get it upstream, and just living with it, and then having a lot of pain when they later need to do a product refresh, a new product update to a later kernel, and none of the changes they've made are applicable anymore. They all have to be redone. But I don't like that perception, and I'm pleased to see that it is starting to change. We no longer see many people who think of embedded Linux as irrelevant to the general case. I think it's accepted to be a lot more relevant now. So, we must prove them wrong. I think we're doing a fairly good job of proving them wrong. We have some success stories. All this stuff works. And it shows the crossover between embedded development and what everybody else wants. I've talked about some of those. Suspended RAM, another important one. Started to become very important to people with Linux laptops only a few years ago. Before that, desktop Linux, laptop Linux, nobody ever cared, or nobody ever at least had the expectation that it might work. They just tolerated the fact that you could never suspend. And SquashFS, which had a lot of use in the embedded space where storage is tight, but it also sees a lot of use on Linux distribution, install CDs, that kind of thing, where again you need to pack a lot of data into a small space. It's just another example. So I talked about, we need to prove them wrong. We need to work better with the community. And these are some of the ways to do that. You find the generic points of interest. Look for that crossover, the ones I've been pointing out. Show why other people would be interested in what you're doing. Show that it's not just something esoteric that nobody but you would ever care about. Show your code, show you're working publish Git trees, sane ones that people can look at, not just a Git tree for your product with every one of the dozens of bits of kernel development you might be working on, but a separate tree for each driver, perhaps for each topic of development, so that somebody who has an interest in what you're doing, somebody you're trying to get engaged with what you're doing to see how it's relevant to them, make it so they can see it easily. It's not just in amongst a pile of other crap that isn't relevant to them. If they're interested in one topic, let them see that and send the patches out for review. And, most importantly, respond to the feedback you get. Some of it is a little unhelpful. There are the whitespace police who will nitpick the most stupid things and ignore the blatant actual coding errors, locking errors, because they don't quite understand that. They can understand the whitespace and they can tell you about that. But, yeah, you have to take that with a pinch of salt sometimes. But respond to the feedback. And the best way to shut the whitespace police up is not to get it wrong in the first place. There is actually I'll talk about that a little bit in a minute. But yeah, there are a lot of people who seem to post some patches, disappear for 3 months, come back again for the next kernel release, want to get their patches merged, and post the same patches again without having fixed any of the problems that were pointed out last time. And that's a very quick way to get onto email blacklists to people, or even just mental blacklists with people saying, I'm just not going to read that patch again. I know it's the same as last time. So really, work with the maintainers, be part of the community. Don't go off and do stuff in isolation, if at all possible. Staying close to upstream. It has its pros and cons. Upstream moves fast, and it is hard to be on that treadmill. But it is, in general, worth it to stay close and to basically minimize your delta between what is in Linus's Git tree at any moment and what you're shipping in your product. Every time I work on something, my viewpoint is getting it to Linus as quickly as possible so that it's not my problem anymore. So that I can just download tomorrow's 3.7 release and it should work. And yes, I have to do the QA, etc., and I might not actually update, but at least I know that when I do a product revision, when I do a new product which is, which supersedes the product I'm working on now, I should be able to start from a mainline kernel with no patches. I shouldn't have to spend weeks forward porting stuff I did months ago that no longer applies, no longer works because somebody else has made changes in that area. So being close to upstream really does make it easier for new products and fixes. So if somebody finds bugs in code that you're using, but perhaps you haven't been dealing with it much, those fixes are a whole lot easier. I appreciate there are some insane people who spend a lot of time backporting code to earlier kernels, but they still tell you that you should update if you can, right? It makes it a lot easier to take in external contributions, so if somebody else is doing some work that you can use, they're likely to be working on a newer kernel as well, so the closer you are, the easier it is to use other people's work and to collaborate with people. And the more likely people are to review and test your code. It just makes life so much easier. But yes, there is a cost inherent in writing code that can go upstream. It is harder. It can, if you're not used to it especially, take more time. If you post code that doesn't pass muster in the first place and you have to review it and go through all the feedback, then yes, that can be hard. And then the second point there becomes even more relevant, that it's a fast-moving target. And if you're having to do these iterations of your own code, perhaps the kernel has moved on by the time you've got your own house in order. So that's hard, and you may have NDAs, you may have problems with information about your product leaking because you're working on certain kernel features. You might have marketing reasons, essentially, why you might not be able to release code sooner. So there are some costs, but I think the biggest one there is that if you get it right the first time, it shouldn't take any longer. It should only be a benefit. And if you get it right the first time, then you should be able to release it later. Now, Android is often a bad example of many things, but they're getting better, and they're getting there a bit. They are using current kernels, and they are relatively aggressive in updating to new kernels and getting their code merged. There is still a fair amount of stuff outstanding, but I think with a stock 3.6 kernel, you can run Android user space. Am I right in that? I think so. So they have finally basically got everything, at least in the staging tree, and they are getting there. So this is, yeah, I talked about this. Find parallel requirements. Avoid hacking around problems. One of the things that a lot of people in the embedded space do is they come from working on another operating system and where they don't have as much visibility into the core OS. And so the assumption is the first thing they think to do is to work around a problem in their own driver. So rather than fixing the infrastructure so that it supports your feature properly and generically, you'll do some local hack. Don't do that. It's a really bad idea to do that kind of thing. It will get your code rejected. We saw a lot of this when I was working on OLPC with wireless mesh networks. And this had been done by Marvell as a wireless driver with some extra mesh support bolted onto the side with special ioctals, which was the wrong way to do it. And so a lot of the work we had to do on that driver, aside from just fixing the code, was defining a generic API for some of the mesh functionality and putting that into the core and then exposing it through the driver in a sane way rather than just having it as a driver-specific hack. Another thing people often get wrong is not caring about locking. Now, this is perhaps less true these days where we have RT preempt kernels. But in the days when people would run embedded devices on a uniprocessor system where spin locks were a complete no operation, you'd see a lot of locking bugs in drivers that would be picked up in review and just mean you have to do more work to go and fix that if you didn't get it right in the first place. The coding style, I talked about the white space police. There is some merit in what they do. If you imagine reading a book, and every time you turn a page, the new page is in a slightly different font with a slightly different layout and borders, that's going to make it slower for you to read. Every time you turn a page, your eyes, your brain is going to have to adjust to reading the new style, and it makes it harder to understand. And that's why people care about stuff that might just seem like gratuitous pedantry. I might suggest that perhaps they don't need to care quite as much as they do, but there is some merit. This wasn't supposed to be this isn't even the right presentation. Joy. I had some more slides with details of some of the white space, some of the coding style errors. Bear with me. Sorry. Sorry, the perils of not presenting with my own laptop. Okay, I give up. I was going to talk, I was going to show, it doesn't work quite so well in voice, some of the problems that we get with patch submissions. There are a lot of things that you should do before sending a patch that are just cosmetic, that you have absolutely no excuse for getting wrong. And I can show you offline sort of an example. I was going to put it up on the screen and say, can you see the 10 errors in this slide? And then I was going to show you the answers. And they were, you know, such things as just white space in the wrong place, but patches get mangled by your email client and you introduce word wraps. When you send a patch, first send it to yourself. Well, actually, before you even send it to yourself, read it. Patches are human readable. You can look at it. You can understand it. You should understand it. But, you know, a unified diff patch is very simple to read. It has lines that start with a space, which are lines of context. They are just what is there, both before and after your change. Lines that start with a minus sign are lines which get removed by the patch. Lines which start with a plus are lines which get added, which are often very similar to the line that gets removed. You should be able to read that. You should be able to understand it. You should be able to look and see superfluous changes. Often, you see patches with a whole bunch of completely gratuitous changes that should not be there. So adding blank lines, adding spaces or whatever in the middle of a line that isn't otherwise changed, it's a mess. It makes the patch hard to read. If you send a patch like that, you have obviously not even read your own email before hitting send. Why would you expect people to take you seriously? So first read your email before you send it. Then send it to yourself. Save the resulting email to a file. Attempt to apply that as a patch. If it doesn't work, go back to step one. Work out why. Work out if you're using Exchange and it's converted all tabs to spaces. Work out if you're sending HTML, if it's word wrapped. Make it stop. And then, yeah, there are a bunch of other things about just abiding by the coding style of the kernel so that people can understand and can read it naturally, and it comes straight into their brain without them having to think about interpreting what they see in front of their eyes, because that's the reason for the coding style rules. It's to make stuff easy to read for the people who spend all day reading it and don't want to try to interpret different styles of code. So there are a few things along those lines. I think I'll try and show the rest of the slides offline if people are interested. So do we have any questions?
Well, sending the patches, I've been trying myself to send patches using Thunderbird.
Don't.
And instead of twisting Thunderbird, my choice was to just git send email.
Yep.
To the same problem.
Yes, very true. Use git send email. That works nicely. But again, make sure you send it to yourself first. Even with git send email, you know, it's useful to read through the patches before you send them. So yeah, that's a good trick to use git send email.
Do you have funny or horror stories about embedded Linux? I mean, you give a lot of examples, but you didn't give funny examples like pacemakers, nuclear reactors, warships, and so on.
No, I didn't. I haven't worked on many things like that, thankfully. I know it's Karen Sandler of Gnome Foundation has been talking recently about her pacemaker, and that's a very interesting presentation if you could get a chance to see that. But no, I haven't even heard particular horror stories about places that JFFS2 is being used that scare me. So no, nothing interesting like that, I'm afraid. Okay, thank you.